Cassian. Good afternoon. I would like to continue with the presentation that has already been started, and I will focus on the reactions which are triggered in the aqueous and also in the wine solution with tartaric acid, methanol with pH which is closer to 3-4. The previous speaker already mentioned the fact that chitosan is a linear heteropolymer formed by randomly distributed D-glucosamine and N-acetyl beta-D-glucosamine. This is the scheme. Therefore, chitosan can be obtained from a number of things: crabs, lobster, shrimps, insect exoskeletons, and the cell wall of fungi, which provides the well-known fact of being allergen-free, non-toxic, biodegradable, biocompatible, and cheap. Chitosan has therefore been exploited in several domains, especially in biomedical applications. And it is also used for water treatment because it helps in removing proteins, and it has also been used due to its chelating properties. As I said, chitosan is capable of having a complexation reaction with several metals, especially iron. Here we have the amine groups that we find in red, and we have the hydroxylic group, which is in yellow, with different pHs which can be produced differently. What we see here are a number of phases of vinification. We see that from the very alcoholic fermentation down to cellaring, there are chemical oxidation phenomena which occur, and they include a mediation on the part of temperature and light, be it natural or artificial, plus the presence of metals and oxygen in the solution. This leads to reactions, including the Haber-Weiss reaction and Fenton reaction, which form reactive oxygen species, O2 giving lead to HOO or the others. The presence of these compounds of course, produces a number of effects, because due to the presence of polyphenols, this leads to semi-quinones, which can then lead to quinones, and by means of polymerization, they can also lead to colored phenols. Or, if ethanol is present, we will have, again, ethanol, due to the very presence. I would also like to add that these species make it possible, due to the presence of metals in the solution, to have a modification of native VOC, which then leads to a decrease in the aroma. In order to counter this problem, a number of additives are used. Addition of antioxidants is one solution, glutathione specifically, and also SO2. Which certainly has an indirect effect. Hence the question, why not use chitosan to trap free radicals? Is it possible to use chitosan to have an antioxidant activity and reaction, be it direct or indirect? And the question then is, can chitosan scavenge reactive oxygen species? Is there a direct action with reactive oxygen species? Well, there are different ways to approach this and measure this. ORAC being one with a pro-oxidant, which AAPH, which leads by thermal decomposition to ROS, which in turn will react with the fluorescent probe and will lead to an extinction quenching, therefore, of the signal. By adding any antioxidant, there will be a trapping of reactive species, and this will lead to, in the end, to stability of the signal. Hence the importance of quantifying the phenomenon and also possible quenching of the signal. And we will do that by using Trolox as a reference. Another approach entails that very simply DPPH is used. It's a stable radical. It is purplish in color. And with an antioxidant, it leads to this compound which becomes yellow, which means that it is easy to read and quantify the trapping phenomenon. I'm referring again to the trapping of ROS. Here you see other results of the study. As you can see, irrespective of the concentration of chitosan, you get to a low equivalent value of Trolox. This is the standard that we used as reference. This very low number entails the absence, basically, of trapping activities of this compound, chitosan, on ROS. And these results are confirmed by the DPPH assay results, because despite the increase in the quantity concentration of chitosan in the soil, you have a reduction in absorbance, and if no yellow color is obtained, then there has been no reduction. It seems, therefore, that chitosan does not show a direct antioxidant activity. For this very reason, we might think and assume that if there is an antioxidant activity, this must occur indirectly by chelation of metals. Therefore, we need to know whether chitosan in the wine solution, in the model wine, has these chelating properties or not. And this is what we did. We used different concentrations of iron. You see Fe3+, Fe2+, and copper 2+. We see, based on this type of approach and analysis, that chitosan can eliminate the compounds in the solution when it is used in higher concentrations vis-à-vis what was done in the beginning. We can also evidence that there is an affinity of chitosan with different metals, specifically that goes for Fe3+, 2+, and copper 2+. Since chitosan can chelate solution metals, we then need to know whether this has an effect on colored compounds. And we did an experiment to ascertain that in order to age solutions in a controlled way. We took a model with tartaric acid and methanol, and we added flavanol, metal ions, Fe2+, Cu2+, and Fe3+, and heated at 40 degrees for 86 hours. We saw that colored compounds appeared in the solution. By preventively using chitosan in the solution, we saw that no color was formed. This, in turn, underscores the preventive action of chitosan, and this in relation to phenomena which otherwise lead to the formation of color compounds. And also another experiment that was done is depicted here, because you see chitosan shows, based on this, an ability to trap paraquinones. So it turns into compounds with other products. In this case, chitosan was added at different levels. So again, there is a double action of chitosan. On the one hand, it acts to the base of the formation of colored compounds with a chelating effect, but also it acts on the colored compounds themselves. If we make a scheme out of this, we see that chitosan can act on colored compounds in this phase, but it can also act at the beginning of the reaction here in this phase of the process. We see, therefore, that all the reactions, tartaric acid, and all the things that you see on the slide lead to what we said. So we need to know whether we can avoid the two compounds which were highlighted. In order to do so, we performed additional tests with the very same model solutions. We added the mixtures of flavanol, and we added iron 2 plus concentrations. This is the species that favors acetylic acid formation. After 86 hours, by means of an accelerated aging process at a temperature of 42 degrees, chitosan reduced significantly the formation of this compound, which is a glycosylic acid. Therefore, in case of high concentrations of this metal species, we had a saturation effect on chitosan, and the action was less effective. Afterwards, we tested an additional aging phenomenon, which is more practical in a way when compared to the temperature used to accelerate aging. And here it is written water, but it is not water. It is a solution, the model solution. And 72 hours exposure to light, half lux intensity. This is what happened. Formation of glycoxylic acid, tartaric acid, and also acetaldehyde. Here we have a significant reduction in the solution in the case of chitosan. I would like to add one thing, and basically I would like to go back to what I said in the introduction with reference to a study that was performed by Dr. Chinnici, who put in a model solution chitosan with different thiol compounds. After 21 days of contact, the solution was dosed, and he saw that using chitosan permitted to preserve thiol compounds much more effectively than in the simple usage of the central compound. As you can well imagine, this in turn made it possible to assess the effectiveness of chitosan in quenching solution metals, which quenches in turn all those reactions that modify volatile compounds. Therefore, there is a preservation of wine aromas. I have told you about reactions. Probably I was too fast, but I would like to go back of what we said about oxidation processes and the direct action of chitosan on solution metals, which produce or can produce radicals. Let's now focus on this radical production, and let's try and understand whether chitosan, by quenching these metals, also quenches or inhibits the formation of these radicals in the solution. We used spectroscopy in order to ascertain that, ESR spectroscopy, and the intent was that of detecting species such as free radicals. This detection was made using RPE methods or using spin spectroscopy. If the radical is not persistent, in the case of spin trapping, so it is not persistent, radical spin trapping was used. Here we see the principle of spin trapping. The radical is trapped and a persistent radical is formed, and this can be detected with the spectroscopy. We have therefore this spectrum situation, which provides us with information on the type of radical that was formed, and also they provide us with additional information on the base radical. Our trap is depicted here. When there is a radical or a free radical, then this reaction occurs and more detectable products are formed. These are detectable by using, again, spectrometry methods. We have carried out several experiments in order to understand whether there was an interaction between chitosan and our solution in water or in the model wine. And we saw that there was no interaction. There was no ESR signal. And instead, if the trap is used in the presence of iron in the water, we obtain this adduct, which is a radical, which gives the spectrum. There has been a trapping of the radical, therefore. If we use the very same metal species in the solution model or model solution, I have the two radicals. One is the former one, and the other one derives from ethanol, and it is providing this type of spectrum. Now, if we associate iron, normally I will have detectable radicals, but if I add chitosan, the signal is neutralized, which means that chitosan is able to form a complex with iron, and this is what I've been trying to evidence from the very beginning, leading to suppress the formation of reactive oxygen species. This inhibitory effect is concentration dependent, and this is very interesting in that you can reduce metals in concentration and also the formation of ROS. To conclude, I wanted to shed light on the fact that using chitosan, you can have an interaction with para-quinones, which are responsible for color shifts in white wines, and it helps preserving thiol compounds better than using SO2. Plus, consider that chitosan is a good inhibitor of metal ion chelation, derived chelation. Let's now summarize everything into a scheme, which is what you're seeing on this slide. There is a preference in the type of pathway, say, proposed by the various metal species in the solution. If I use chitosan, I act on all of them, plus also on colored compounds themselves, which means that I can suppress all the reactions that lead to the formation of colored compounds. And now I would like to give the floor back to Dr. Robillard, who will conclude on this topic. Thank you, Mathieu. I would like to show to you a number of comparative applications. I kindly ask you to go back to the presentation. I need the slides. Thank you. There is a right slide on my computer screen, but it is not there. Well, there it is. I would like to show to you one of the comparative analyses that we made with a product that can be classified as products which are opposed or which counter the oxidative properties of wine. We see casein, P protein, PV, PP, and NOx, which is a chitosan-based formulation. Here we have optical density at 420, 520, 620 nanometers, which is a good marker of the coloring of the wines. The trials are performed using the same quantity of product, and the dose is 30 grams per hectoliter of must. This is the reading of the color yellow on the y-axis, and we have red on the x-axis. Here we have the proteins, potato proteins, PVPP, this was the control, then P protein plus PVPP, P protein alone, and then we see the two best products, which are casein, which certainly should be very proud of its results, and the chitosan-based product, which has been called an QI NO-ox. So, to conclude, I must say that we're very positive about this product because we developed applications, those applications that have been shown, which evidence that chitin derivatives can be very good products in flotation, in the decontamination of wines. We have a very recent formula that was launched last year, and it is a product to decontaminate wines vis-à-vis heavy metals such as iron, but also lead, cadmium, and aluminium. And then the antioxidant properties that were illustrated by Mathieu, they are also very interesting and should be remembered. I think that we covered the topic under the title of our contribution. Chitin derivatives are innovative products. They are in line with current expectations. We are convinced that in the future an increasing attention will be devoted to healthy wines, and we think that chitin derivatives are products that can be very helpful in order to achieve that. Thank you for your attention.